All right, guys, welcome back. I hope you're having a great day. So, today we are going to start the second half of chapter 3. The first half was all about looking at the model of the atom. The second half is going to be looking at a way of counting the number of atoms within a substance. Okay, so we're going to be looking at a new way of counting, particularly looking at atoms. So, before we get into the new material, we're just going to review some previous units of counting that we're already familiar with. The first one being a dozen. So when you think of a dozen eggs, a dozen donuts, you automatically think of the number 12. Okay, so whenever you see dozen, you think of the number 12. Likewise, whenever you see a pair, like a pair of socks, a pair of students, you automatically associate that with the number 2. And then another common unit of counting is going to be a ream. And this is pretty common with paper. Whenever we refer to a ream, we're talking about 500. So a ream of paper would have 500 sheets, or 2 reams of paper would have 1,000. The unit of counting that we are going to be using in chemistry is referred to as a mole. For a mole, we are going to use the number 6.022 times 10 to the 23rd. This is kind of a long number to say. We also refer to it as Avogadro's number. So whenever you see 1 mole, you're automatically going to think of 6.022 times 10 to the 23rd. Okay, so look at some examples. If we have a mole of atoms, that means we have 6.022 times 10 to the 23rd atoms. You have 1 mole of molecules. That means you have 6.022 times 10 to the 23rd molecules. If you have 1 mole of M&Ms, you have a boatload of M&Ms. You have 6.022 times 10 to the 23rd M&Ms. Likewise, 1 mole of puppies. How many puppies would we have? You got it. 6.022 times 10 to the 20th. Okay, so we are basically going to be able to use this as a new conversion factor. Okay, so 1 mole and 6.022 times 10 to the 23rd are going to be the same thing. And since they are the same thing, we're able to use this as a new conversion factor. Now that we have this new conversion factor, so 1 mole is equal to 6.022 times 10 to the 23rd, let's get some practice using it. So in our first example, we have 4.5 moles of hand sanitizer bottles, and we want to figure out how many bottles of hand sanitizer we have. Okay? So remember, when we're doing our dimensional analysis, we never start with the conversion factor. So that means we're going to start with what we're given. We're going to start with our 4.5 moles. Okay? We need to multiply that by a conversion factor that will cancel out moles and leave us with bottles. Thankfully, we have this new equality statement or conversion factor that 1 mole, so 1 mole of hand sanitizer bottles is equal to 6.022 times 10 to the 23rd bottle. Okay. So we have moles on top, moles on bottom, so that they cancel out and we're left with bottles. If you guys remember, we're going to multiply by everything that's on top and divide by everything that's on bottom. So in our calculator, we do 4.5 times 6.022 times 10 to the 23rd. And we would find that we would have 2.71 times 10 to the 24th bottles of hand sanitizer. Think of how clean you could get with 2.71 times 10 to the 24th bottles of hand sanitizer. Save the world with that. Okay. So let's look at one that's a little bit more scientific. So let's say in this example, we have 5.75 times 10 to the 23rd atoms of krypton. And we want to figure out how many moles that is. So again, we never start with a conversion factor. So we are going to start with what we're given. So 5.75 times 10 to the 23rd atoms. We don't want atoms though. So we need some way of canceling that out. So if atoms is on top to start off with, that means I need atoms at the bottom of my conversion factor. Thankfully, again, if we're trying to go from atoms to moles, we know in 1 mole of a substance, we're going to have 6.022 times 10 to the 23rd atom. They have atoms on top, atoms on bottom. They cancel out, and we're left with moles. So here we would do 5.75 times 10 to the 23rd divided by 6.022 times 10 to the 23rd. This is where it might be useful again to use that E button. So in our calculator, we might want to have put 5.75 E to the 23rd in place of the times 10. Just don't have to worry about parentheses. But we should find here that if we have 5.75 times 10 to the 23rd atoms of krypton, that's the same thing as 0.955 moles of krypton. Okay. All right. We are going to do 2 more examples, these conversions, and we're going to try these by yourself. Okay. So in this first one, we have 0.75 moles of water molecules, and we want to figure out how many water molecules we have. So using that conversion factor, go ahead and pause the video and try and figure out how many water molecules you would have in 0.75 moles. All right, so we are going to go ahead and check to see what we got for our answer here. So again, we're using our conversion factor that 1 mole is equal to 6.022 times 10 to the 23rd. So we never start with a conversion factor, so that means we'll start with our 0.75. And then in this case, we're going to multiply by our 6.022 times 10 to the 23rd molecules for every 1 mole, so that we have moles on top, moles on bottom, and they cancel out. So when we plug this in our calculator, we should find that we have 4.52 times 10 to the 23rd molecules. Okay. Awesome. Likewise, do the same thing for number 2. Go ahead and pause the video and come back when you have your answer to see if you did it correctly. So for our second problem here, we should have found that there is 0.00364 moles and 2.19 times 10 to the 21st atoms of calcium. Again, here we wanted to divide because if we have atoms on top and atoms on bottom, then we were able to cancel them out. So if you got this as your answer, give yourself a little pat on the back. Awesome job. So then let's take a look at what a mole actually looks like. So we've talked about a mole being 6.022 times 10 to the 23rd particles. So in this picture, we have a variety of substances. And in each beaker, we have a mole of that substance. So if we notice, our mole of mercury 2 oxide is a lot smaller than our 1 mole of sugar. Likewise, our mole of copper is a lot smaller than our mole of copper 2 sulfate pentahydrate. Okay, so 1 mole of different substances, or 6.022 times 10 to the 23rd particles of different substances, are going to have different sizes. Okay, and this has to do with the size of our particles. Okay, so if each one has 6.022 times 10 to the 23rd particles in it, it's reasonable to assume then that our sugar particles are going to be bigger than our mercury 2 oxide particles because our sugar particles take up more room. Okay. So we can actually find how many grams are in 1 mole, or 6.022 times 10 to the 23rd particles of an element or compound. And this is going to be given as grams per mole. Notice that per there, that should jump out because we're going to be able to use molar mass as a conversion factor. And this is what we're going to look at tomorrow. Okay. So to find our molar mass of a substance, all we have to do is look at its atomic mass on the periodic table. Remember that atomic mass is the decimal underneath that chemical symbol. Whatever that atomic mass is, that is how many grams we have per mole of that substance, or how many grams we have in 1 mole. So for instance, if we look at the periodic table, the atomic mass of Mg is 24.31. Okay? That's that mass we got from the periodic table. That means if we have 1 mole of magnesium, it's going to have a mass of 24.31 grams. And we know 1 mole is 6.022 times 10 to the 23rd atoms. So that means if we have 24 grams of magnesium in front of us, that means we have 6.022 times 10 to the 23rd atoms in that substance. So that is a lot of atoms within a relatively small sample of magnesium. This is why the unit of the mole is so handy, okay? Because we have so many atoms within a substance because they're so tiny, we need an easier way of counting them, okay? So again, that periodic table will tell us how much 1 mole, or 6.022 times 10 to the 23rd particles of that substance weigh. So this just goes to reiterate the fact that since we have different masses on the periodic table, different elements and compounds are going to have different masses within 1 mole. Or 6.022 times 10 to the 23rd particles of a substance are going to have different masses because on the periodic table, we see that some elements are more massive than others. They're just bigger. All right, so let's look at some examples of finding our molar mass, or how many grams we have per mole. Remember, molar mass is grams per mole. Okay. So when looking at boron, to find the molar mass of this guy, we just want to look at our atomic mass on the periodic table. And if we look at our atomic mass on the periodic table, so that number underneath the B, we are going to see that our atomic mass is 10.81. That means 1 mole of the substance has 10.81 grams. Okay? Or 6.022 times 10 to the 23rd particles of the substance have a mass of 10.81. Okay? We can do the same thing when we have a compound. So in our second example, we have H2O. So in this case, we have 2 hydrogens and 1 oxygen. So here we're going to do the same thing. We're going to find what our atomic mass is for hydrogen and what our atomic mass is for oxygen, and then add them together. Okay? So if we look at hydrogen on the periodic table, its atomic mass is 1.01. And again, we have 2 of those. So we need to take into account how many of that atom we have. Oxygen, that's going to have an atomic mass of 16. So when we add these together, we'll find that H2O in total has a molar mass of 18.02 grams per mole. Okay? So we can see that 6.022 times 10 to the 23rd particles of water of H2O is going to weigh more or have a greater mass than 1 mole of boron. Okay? Because those particles are more massive, they're bigger. All right, this last one is a little tricky because we have these parentheses. Remember, when we have these parentheses, this is saying that we have 2 OHs. Okay, so that means in this formula, we have 1 calcium, 2 oxygens, and 2 hydrogens. Okay, so if we want to find the molar mass of the substance, we need to find the masses of those individual elements and add them together. So calcium is going to be 40. We get that from the periodic table. From the periodic table, oxygen has a molar mass of 16. The hydrogens have a molar mass, again, of 1.01. So when we add those together, we'll find that CaOH2 has a molar mass of 74.02 grams per mole. So 74.02 grams of calcium hydroxide and 1 mole of calcium hydroxide are the same thing. Okay. Where we need to just be a little bit more careful is if we were to have something like NH4 2 SO4. So in something like this, remember this is saying that we have 2 NH4s. So that means in total we have 2 nitrogens and 8 hydrogens. So just be careful with those parentheses when you're calculating your average atomic mass. Okay? So I hope this was helpful. Please let me know if you have any questions. Otherwise, I hope you have a great day.